All right, so exam 2 is a week from today. So Tuesday, the 18th. I'll definitely get exam 1 back to you on Thursday. And the topics for this one, let's go up through two-dimensional rigid bodies. So today, so this will be up through 2D, well, I guess what it's called is rigid body statics. Number 8. So that's the two-dimensional stuff. Okay. Number 9, it starts with I think that's what I just saw. That's not working. Okay, so if you go to rigid body statics, 7, 8 are 2 dimensions, and then number 9 is new stuff. We won't do that for the test. So just up through the stuff in number 8. Okay, anybody have any questions about the test? Yes? Yeah, it's all cumulative, so you should make sure you're comfortable with the old stuff too. Any other questions? Cumulative as in the density of the question, right? Or throw in a question from... Right, I can throw in old questions. Okay. So yeah, you should just always be trying to make sure that you remember how to do the old problems too. So the problems will never be, I'll never combine topics in a way that isn't in the assigned problems. The problems will all be similar to the assigned problems, but they'll always go all the way back to the beginning. Okay. Any other questions? All right. So last time, we talked about two-dimensional joints. And I broke that discussion up into how many degrees of freedom are restricted by the joint. So those were the different categories. There's sort of two ways to approach this. The first one is, I gave you the list of all the joints, all the two-dimensional joints we'll see in this class. So one thing you could do is just remember the different joints, and then it doesn't take any thinking really. So you could memorize the loads applied by each joint type. The second way to do it is to think about that joint connecting the body to the ground, and think about what degrees of freedom are eliminated by that joint. Translations, there's 2 dimensions of translation and then 1 rotational motion. So you could also think about the eliminated degrees of freedom. The best way to do it is to sort of do a combination of both of those 2 things, because it gives you a sanity check on it, you know, like you can look at it and say, and just like remember how to deal with it, and then think like, does it make sense? Am I thinking about it right? You know, it makes it much more likely that you're going to catch a mistake in dealing with a joint. Those the 2D joints, the list of 2D joints from Thursday. So, you know, memorize it and make sure it makes sense. In my opinion, like in any kind of engineering stuff, you're always looking for ways to verify what you're doing, you know, because, you know, making mistakes can be really bad. And so you're always looking for sanity checks on the ways you're approaching stuff. And if you have 2 different ways to do something, it's so useful as a way to make sure that you're doing it right, you know. And you don't always have that. When you do, it's a nice luxury. That's how I think about it, you know. And well, I spent 3 years working in this biomechanics lab in a hospital where there was no one checking my, you know, there was no one to check my work. I was the only person there, you know, and so I needed to make sure that what I sent out was right, you know, and the calculations and the programs were right. And I feel like most of my job really was thinking about how I was going to verify the calculations that I did, you know. How could I come up with a way to independently verify so that I didn't send something out that some surgery was going to be based on, you know. So anyways, redundant ways of doing things are super, super useful. You know, I think it's easy to get away from that when you're in classes, or to not be aware of that when you're in classes, because you just sort of write down everything you know, and then they tell you you did 80% right or whatever. But when you're really doing engineering, that stuff is so crucial, you know. All right, so today let's do a bunch of examples. Okay, so for the first one, let's say we have an object that's connected to the wall by a fixed joint. Let's say this angle is 50 degrees. And a cable is connected to the end of this beam that goes over a pulley. And the other end is connected to a mass of 200 kilograms. The length of this beam is 2 meters. And something we're going to do a lot of times, and we're going to do here, is we're going to assume that that beam is thin enough that we don't have to worry about the, the thickness of it or the width of it in this calculation. So we'll just assume that that it sort of makes a line and that cable is connected to the end of the line. And let's say that the mass of the beam is 100 kilograms. And we want to know the reaction loads at the wall. Yeah. Okay, so first thing we have to do is draw a free body diagram. And I guess let's first do a free body diagram of the mass and figure out, we'll see that we can calculate the cable tension with that. It comes out just like you'd think it does, but I feel like okay, this is my second like soliloquy of the day, but this is sort of an important thing. So most people do statics before they do dynamics. And it's nice because, that's a nice way to do it because you learn how to deal with the left side of Newton's second law and the moment equation without having to worry about the right side that has the accelerations and stuff in it. But there's some places where it makes you sort of sloppy. There are two main places that I can think of. And one of them is in stuff like this. In a statics problem, the tension in this cable is exactly equal to the weight of that mass. Okay, and so you get used to just sort of like glancing at it and saying like, okay, skip that, and you just know that the tension in this cable is 200 times 9.81. So that would not be true if this was accelerating. Okay, if this was a hinge and this and everything else was the same, and so this was making this beam accelerate up, the tension in this cable would be less than 200 times 9.81. So I think sometimes I probably take that shortcut too, but I try to remember to not make assumptions about what kind of tension you have in cables and stuff in setups like this. If you get in that habit and then you go to dynamics where things are accelerating, it'll lead you astray, Okay, so for the mass, we have 200 times 9.81, so 1962. And then we have the cable force up. And Newton's second law says 0, negative 19.6, 1,962. Plus 0t is equal to, well, for us it's going to be 0 because it's statics. But you can see it right here. Like, notice what would happen if there was a vertical acceleration there. T wouldn't be equal to 1962 anymore. Okay, so you got to be careful about that. Generally speaking, in statics you barely have to be careful about anything. But that's the good and the bad. Okay, so the x equation doesn't say anything, but the y equation says t is equal to 1962. So now we'll do the free body diagram of the beam. This is the new stuff. At the center of the beam, we have a weight force down that's equal to the mass of the beam times 9.81. So that is 981. And then we have the cable force, and we just calculated that the magnitude is 1962. And now this is the first time in one of these problems that we're using what we know about two-dimensional joints. So with that fixed joint at the right end, is there any axis where this can translate? No, so the X and Y components both have forces applied, okay? There's no axis where it can translate. Can it rotate? No, so a fixed joint eliminates all, it eliminates all 3 degrees of freedom, and that means it's gonna have 2 components of a force and a couple. So I'll write that as, I'll call that force R, reaction force, and then I'll call this couple MR, reaction moment. And now, so I didn't do this when we isolated the mass because that I just did as a particle. We weren't dealing with rotations of that mass. But this is a rigid body. We do care about rotations. We're dealing with moments and stuff. So I'm gonna write out the cable. Rho vector, force vector, and moment vector. And now we have to choose what we're going to calculate the moment about. And you can choose any point you want. I'm going to choose this point here, but any point would work. That's the other place where statics makes you a little sloppy, because in dynamics, you only have a couple of choices about where your about point can be. In statics, it can be anywhere. Okay, so the red is the about point. And let's just go through all these loads and fill out a row for each one. So first I'll deal with that reaction force R. The rho vector is the vector from the about point to where the force is applied. So what's that in this case? Yep. So 0, 0, 0. For the first couple of these, I'm going to write it all down as components, and you'll see patterns with those as we go. And the R vector is Rx, Ry, 0. And cross product then is 0. Next, I'll do the couple MR. For a couple, you don't care about these. That only has a Z component, so this is 0, 0, MR. And now I'll go to the weight force. So we have to figure out a vector that goes from the about point to where the weight force is applied. That's the center of the beam. So to do that, I'll draw the coordinate system. And first on that coordinate system, I'll draw the vector where that angle is given. Okay, so we know that it's 50 degrees from a downward vector like that to a vector over like this. So that's what I'm going to draw. Okay, so from the negative y-axis to this is 50 degrees. Yeah, so now the angle that we want is from the positive x-axis to this. So that's 270 minus 50. So that angle is 220. The length of the cable, the length of the beam is 2 meters. So the distance to the middle of the beam is 1 meter. So for the weight force here, we have 1 times cosine of 220, 1 times sine of 220. That is negative 0.766 and negative 0.643. The weight force is 0, negative 981, 0. And the cross product between those two is 0, 0, and then a z component of 751.4. Yeah, that's the, we know that's the distance from here to here. Yeah, exactly. That's what it is. Yes. Yep, it's just a vector version of that where you don't have angular acceleration. Let's see. And then we have the 1962. So that's going to be 2 times cosine and sine of 220, or twice this. So that is negative 1.532, 1.5, and negative 1.286. And then 0. The weight force is 0, positive 1962, 0. And the cross product is 0, 0, and then a z component of negative 3790.6. Okay, so now that we have all these forces and moments, that's all the loads in the free body diagram. Now we're going to use Newton's second law that says add up all the forces, and that has to add up to 0. And we're going to use the rotational Newton's second law, the moment equation, that says add up all the moments about A, that also has to be equal to 0. Okay, so that's what we're going to do now. So first, Newton's second law. We're going to take all of the forces here, and that's going to be the left side of Newton's second law. So we have Rx, Ry, 0, plus 0, negative 981, 0, plus 0, 1962, 0, and that's all the forces, are equal to 0, 0, 0. Yep. No, pretty soon I'm gonna stop including that too. Um, but I want to do at least one where you see how it just ends up being, uh, like in a way, everything is a three-dimensional problem. It's just certain components just end up being useless, you know? Okay, so from this, you get that Rx is equal to 0, Ry is equal to negative 981. Rz is 0. And so that reaction force is 0, negative 981. I'll leave the Z on there for now. Newtons. Okay. And now the moment equation, the torque equation. By the way, you said the torque equation. Physics people tend to use torque and moment interchangeably. In structural engineering, in mechanics, people don't tend to use torque that way because the torque is a specific, it's a equal and opposite moment on two ends of a rod, you know, something that would cause a twisting stress on it. So anyways, I'm gonna always use moments, but yeah, in engineering, it has a specific thing. Physics people, it doesn't, because they don't care about specific things. Okay, so now we're going to use the moment equation. And so we're going to add these up. So we have 0, 0, 0 plus 0, 0, MR, that's the couple, plus 0, 0, 751.4 plus 0, 0, negative 3790.6 and we got these from that column of the table. And these add up to a 0 vector. The first two equations don't help. But the third equation says MR is equal to 3790.6 minus 751.4. So I think that's 3039.2. It's all in SI units, so that's Newton meters. And the positive means that that moment is counterclockwise. Okay, so the net effect of all these forces. So let's think if that makes sense. So you have a little force with a little moment arm that's trying to make this rotate counterclockwise. Okay. You have a big force with a big moment arm trying to make it rotate clockwise. And so the couple at the wall has to counteract a total, tendency to rotate this clockwise by providing a counterclockwise couple. Okay. And that couple, like what is that couple? Again, remember that means you can think of that as two forces. This is counterclockwise, so it's a force going this direction at the top of the beam, combined with a force, equal and opposite force going this direction at the bottom of the beam. And together Yeah. So right here. Okay, so how did we get that? So we figured out that to go from, well, let me draw the vector. So that vector is like this, right? We're trying to get the vector from the about point to where the force is applied. And we know that the length of that vector is 2 meters because the beam is 2 meters. And we know that the angle is from the x-axis to the vector, that's 220. So it's going to be 2 times cosine and sine of 220. Yep. One thing that's useful, oh, dang it. Oh, I know what to do here. Okay. One thing that's useful a lot of times, surprisingly often, is if we would have first calculated, the vector to here, okay, then we know that this is just going to be the midpoint of this vector and 0. You can always find the midpoint between 2 points by just averaging the coordinates. You ever notice that? It comes in handy really often. So if we would have done this row vector first, the one we were just talking about, and we know that the row vector for the about point is 0, we could have just averaged those 2 vectors, and that would have given us the row vector for where the weight's applied. Any other questions about this one? Okay, let's just keep rolling. Okay, so this time, let's say that there is a wall and a beam is connected to the wall by a pin joint. And this beam is horizontal. And then there's a pin at the center of the beam that slides in a slot. And that slot is in something that's fixed to the ground. Okay, so all of this shaded stuff is fixed to the ground. Okay, you follow that? And then there's a 1,000 Newton force applied to the end of the beam. And this angle is 45 degrees, and that's also the angle of the slot. What really matters is the slot. And the question is, what are the reactions at the 2 pins? In the middle? Yeah, right. So if there were no other connections to the ground with this beam, this thing could slide on, could go up and down, and it could also spin around. And let's see, the mass of the beam also, there's, let's say this beam has a mass of 50 kilograms. All right, so first we'll draw a free body diagram of the beam. Oh, I didn't give a length, did I? We need a length. 1 meter. Okay, so what kind of loads are applied? Well, there's a weight acting at the center. That's 50 times 9.81, so 490.5 newtons. And there's a 1,000 downward at the end. And now there are 2 joints in this one. We have to think about the loads that each of those 2 joints applies to that body. So first, let's think about the pin on the left side. So a pin joint like that, is there any axis where translation is allowed by that pin? If you think of that pin as connected to the ground? No, that beam could rotate, but you couldn't move that point this way or any direction. Okay, so that means there's a full vector of forces applied by the pin. So I'll call that, so there's a full unknown vector, I'll call that RL for left. And now let's think about rotations. Could that beam, so in each of these cases, you have to imagine that everything else is gone. The only thing connected to the beam is this pin. Would this be able to rotate? Yeah, and so there's no couple applied. Yeah, could you rotate? Yeah, spin. Could you spin this thing around that hinge? And you could. So there's no couple applied. Yes. Every time you're only thinking of that individual joint, nothing else is going on. Yep. Into a different spot. Yeah. So the yeah. Now here number 1 are force applied on axis. Right. Okay. And so now we'll go to this one. And again, you have to imagine everything else is gone. If this was the only thing, this was connected to was this joint connected it to the ground, is there an axis where it could slide? And yeah, it could translate along that slide. Okay, so we know there's no force, no component of a force in that direction. Okay, but it couldn't translate perpendicular to that. Okay, and so there is a force component perpendicular to that slide. And it doesn't matter which direction you choose. So I'm going to just sketch this slot in. This is at 45 degrees. And the force is perpendicular to that. And I'll call that RR. That's a scalar because we know the direction. And now we have to think about rotation. If everything else was removed from this problem, would this beam be able to rotate around that pin? Yeah, I mean, that pin can spin inside that slot. So there's no couple applied. Okay, so now how many variables do we have? This is a complete free body diagram. This can tell us whether there's a chance that we're going to be able to solve this by statics or whether there isn't. Yep. Yeah, so we know that there's no force component along the slide because it can slide. Okay, so if there's no force component along the slide, then the only possible point we can check, can it translate perpendicular to the slot? And no, the slot holds it in place at that point. You can't move the pin this way or that way.
Like a force in the direction of where it can go.
Yeah, exactly. That's always the idea. Yep. So you're always trying to think of where it can't go, and that's the direction that the force is applied. Yep. All right, so do we have a chance of solving this problem? Well, yeah, because how many equations do we have for Newton's laws in 2D? We have 2 for Newton's second law, 1 for the moment equation, so 3 total equations. That means we can solve for 3 variables, and that's what we have, 2 components of RL and 1 of RR. Okay? And so now I'm going to write out this table, row, force, moment. And this time when I do it, just to save 10 strokes, if you look at the one above, you saw that for 2-dimensional problems, the z component of rho and f are always 0. And the x and y components of the moment are always 0. So you might as well just give the x and y components of these two and the z components of that one. And so that's what I'm going to do. Okay? But remember that the moments really are, moments are always a vector, and these are always z components of vectors that I'm giving. Okay. All right, so we have to choose an about point. I'm going to choose this, but you could choose anything.
Why do we choose that one? Do you have like a strategy?
Kind of. It really doesn't matter that much, but sometimes if you put the about point at the place where you have the most unknown force components, it'll uncouple the system of equations, and you can solve it equation by equation instead of solving it as a system.
Okay.
So if you put the about point here, you probably have to solve a system of 3 equations for 3 variables. If you put it here, I think what we're going to see is that you can use one equation to solve for this, one to solve for this, and one to solve for this. Yeah. Yeah. Right. Yeah. So it just gets it out of, it just gets a bunch of forces out of the moment equation. Yeah. Yeah. Okay, so the first load I'm going to deal with is RL. The row vector is 0, and I'll leave off the z component. And the force is RL, RR. And now you can think of the cross product as just this times this minus this times this. Whoops, I did that wrong, sorry. This should be RL. RLX and RLY. That's what happens when I'm like talking while I'm trying to think of what I'm going to say next. Okay, but the cross product, 0 times this minus 0 times this, so 0 moment. And remember, that's a z component, really, but I'm giving it like it's a scalar. And then we have the weight force. The vector from the about point to where the weight is applied is positive 0.50. And the weight force is 0, negative 490.5. And the cross product is negative 245.25. And then we have RR. That's happening at the same spot as the weight, so that row vector is also 0.50. Yeah, we do, exactly. Okay, so to figure out that vector, I'm going to draw out the coordinate system. And first, I'm going to draw the vector where the angle is given. So that 45-degree angle is given between the horizontal and a vector like this. Okay, so like this one would have a theta of 45 degrees. Does everyone see how that relates to what's given in the picture? And now the vector we want is another 90 degrees counterclockwise from the one I drew here. So now I'm going to draw this one, the one we want. And we know this is 90 degrees. And so theta for this is 45 plus 90. So 135. And so yeah, 135. So we have, so this vector is going to have a magnitude of RR. So it's going to be RR times cosine and sine of 135. And that's negative 0.7071 RR, positive 0.7071 RR. So then that's the force. And now the cross product is positive 0.3535 RR. And then the last one is the 1,000 Newton force. The row vector for that is positive 1, 0. The force is 0, negative 1,000. The cross product is 1 times negative 1,000 minus 0 times 0. So that's negative 1,000. And now Newton's second law, just add up all the force column things and set those equal to 0. Rotational equation, add up all the moment column things and set those equal to 0. So Newton's second law says RLX, RLY plus 0, negative 490.5 plus negative 0.7071 RR, positive 0.7071 RR, plus 0, negative 1,000, 0 is equal to zeros. And you can't solve for anything yet. And now the moment equation says negative 245.25 plus 0.3535 RR minus 1,000 is equal to 0. So you can use the moment equation right away to solve for RR. And you get 3522.6 newtons. And then plug that value for RR into Newton's second law. And for RL, you get 2490.9 in the x direction and negative 1000.5 in the y direction. Any questions about that? Okay. Well, I'm going to say one more thing, and then I'll stop here for today. On Thursday, so I'll give you some problems like this to work on. And so you can, bring questions if you have questions working on these on Thursday. And we'll just spend time working on this. I'll give you time to work on stuff in groups and then make sure that it's making sense. Okay, this is the last material that's going to be on the test next Tuesday. So, okay, the last thing I want to say is, in the solutions, to the problems that are on D2L, my tables look like this. P, A, row, force, moment. I haven't corrected those yet in the solutions. That's the way I used to talk about it. And, you can do it this way where P is, that's the coordinates of where the force is applied. A is the coordinates of the about point. And then you just subtract those two and it gives you rho. Okay. I think that's sort of unnecessary, so I don't talk about it that way anymore. So just when you look at the solutions, compared to the way I do it in class, you can skip these two, everything else is the same. Yes?
So are all the kinds of joints paired in for the pedal supply?
Yeah. Yeah, all the 2D types.
All the 2D types?
Yeah.
And that's just all the ones you listed on the last time.
That's right. Yep. Yes?
So we're looking at 3D.
Right. Any other questions? Okay. Well, actually, the homework is already posted, so you can work on some of those problems. I definitely recommend trying to work on those before Thursday, and come with questions on Thursday, and we'll just work on this the whole time. Okay.